All right, hey, Doozer Shop here. More with the Hendey tailstock quill, spindle, ram. I got it fitting very well inside the tailstock. Let's go handheld and just start showing, because ain't nothing to it but to do it. All right, let's go. All right. Don't drop the camera, Doozer. All right. So the lapping worked very well. Oh boy, that was super. Thanks again to Brian Block. He had the suggestion, and that was just, you know, that's why I appreciate the YouTube community, especially the, you know, people that follow my channel here, with these good suggestions that. So, man, if you could just, I got my thumb, I'm doing it, but it's tough. All right. Okay. So, you can see the keyway is at the bottom. Can you see the, yeah, it's mostly lined up, but you get an idea of what I was up against. Originally, before I honed it, before I honed the barrel, the spindle, the quill, more, with the tri-lobe of the spindle, and it was probably an egg shape of the tailstock itself. I couldn't tell if it was egg-shaped or tri-lobed, but for whatever reason, these things are such a tight fit. And I mean, I think this is a 2 to 3/10 fit. So that's 0.4 zeros and a 2 or 4 zeros and a 3 inches. It was only would line up there, and that was my fault. I had planned on cutting the keyway, figuring out where to cut the keyway by inserting the quill into the tailstock, marking the bottom where it fits the best, and then cutting it. Well, I didn't do that. I cut the keyway on the highest one of the 3 tri-lobes. Anyhow, the honing, the OD honing of that bar of the spindle, it worked out so well. And you know, it's still a push fit. I can try to, you can kind of see, I'm going to push it, I got to hold it and push it. It's lubricated with mineral spirits now. Oh, look at that. I mean, there is zero perceivable shake. I mean, there's nothing. And it actually gets tighter right there. I mean, it is a vacuum seal, airtight situation, right? I mean, it is just amazingly a good fit. So let me give you a side shot. Like I said, that's flush at the front. That's about 10 inches, the tailstock body itself, and it sticks out another 9 or 10 inches there. So even with it out, oh yeah, let's just push it, if it'll go. You gotta give it a little love tap. So even with it flush at the back, it's sticking out 10 inches, right? And it used to be with the old sloppy tailstock quill, when it was only 10 inches long. So when it was sticking out 5 inches, it only had 5 inches inside the body. So you were half supported and half sticking out. Now, the way I've got it engineered, you're fully supported when you're sticking out, you know, 10 inches. So I'm doubling my stroke right? Instead of 5, I'm coming out 10, and I'm doubling my surface bearing area of the length. Instead of being inside by only 5 inches, I'm inside by 10. I know that's a lot. But, and then of course, that's my extension piece that's going to screw on to those threads that I made on the outside. Man, I cut myself. Where the heck is it? Yeah. Those threads are so sharp. I cut myself just doing that. I was trying to do something and yeah, no problem with that. Okay. So that end's going to have an Acme bronze nut, you know, in bored into the spindle. And of course the front is going to have a 2 Morse taper bored into there. Now, I thought of options. I could bore and with a taper attachment with a boring bar and grind with an internal cylindrical ID grinder a native Morse taper 2 directly into the quill. I could do that. I have the capability. I have, of course, the mighty Pratt & Whitney lathe with the super awesome taper attachment. Well, it's there. To rough it out, and then as a final finish, I could, it'd be a chore to hold in here, but I could do it. Oh, I need a steady rest with this. Oh, I don't have a steady for this. I got one for the 13. See, this is a swing down internal ID grinder, internal diameter grinder, with this Covell grinder. I have one, see, this is a nice electric separate one. I have a belt driven one, actually I got 2 of them, for this Brown & Sharp 13. But I don't have the mounting plates made up, and I don't have the belt and the pulleys made up yet. But I do have the steady rest, so it would take a bit to do it that way. But I'm not going to do it that way. What I'm going to do is use an insert, okay? Let me pause a minute. So the original 10-inch long quill is this, right? And oops, and there's your Morse taper 2 socket, and then the back end. I got the screw installed, but you get the idea. There's the bronze nut. So it's got a Scotch key in there. I don't know if it's called a Scotch key or a Dutchman. It's just a set screw on the parting line. And somebody apparently, before I got this lathe, has replaced this nut before, because there's another where you abandon the old one, the old Dutchman there, or Scotch key. I think it's a Scotch key. I forget. Leave in the comments. And that's how you know, you secure the Acme nut. Now this is 8 threads per inch, actually, and the new 1/2 inch Acme that I bought, it's on order from Roton.com. Roton, they got Acme stuff. So this is 8 threads per inch. The other one's going to be 5 threads per inch. It's a little quicker. So this is 1/8 inch per rev. The one I'm going to buy is 200 thou per rev. So it's a bit faster. Actually, it's a 2-start 10, which is 5, essentially, threads per inch. Okay, that's the 10-inch one. That's the old one. This is the sloppy one. It's very sloppy. Don't want a sloppy quill. No, don't do it. Okay, so back to what I was talking about. For an insert, I could use a couple of different things, kind of like you can purchase these. I happen to have a couple. So this is 2 Morse taper, ground beautifully on the inside, and I think this is 1.25" on the outside. And the nice thing is they got a slot in case you wanted to use a drill bit with the tang, right? What are you talking about, Doozer? Oh, I don't have any Morse taper drill bits in here. I don't think. No, I don't. Something with a tang. Yeah, okay. So here's a reducer from, what is that, 3 to 2? Yeah, there's 2 on the inside, 3 on the outside. But it's got this tang, and most drill bits do. It's got 2 tangs, one's internal. But a drill bit would be solid with that tang. And, you know, when you put it in, it's not going to go in because it's 3. It keeps it from rotating as a little added safety bonus, right? Most lathes do not have this anti-rotational feature. So anyways, the plan would be to use this and maybe turn this down a bit because there's a lot of meat on the periphery there, and bore a straight hole in the tailstock ram with maybe either a light slip fit or a 1,000th clearance fit. And the reason I say 1,000th clearance fit is to use green Loctite, you know, sleeve and bearing Loctite. Hey, here's some. This is good stuff. 620 green. You know, they got green, they got red. But that stuff holds like, you know, a battleship. I'm telling you, that stuff is great. And why am I leaning towards this idea? Because if you bore out, if I were to make a press fit hole, a press fit socket bore in the tailstock quill, when you press it in, it hoops, it gets bigger, right? If you do a press fit and you jam this in an interference fit where the hole is smaller than the size of this thing, it's going to bulge the outside of that tailstock quill, spindle, whatever. And it's such a tight fit, any bulging will result in it, you know, not fitting in the bore of the body. So to recoup, I like the fact of the insert because I don't have to set up and try to make this precision ground socket for a Morse taper 2. If I use one of these, I get a tang, positively located tang feature for using drill bits so they won't spin with one of these. I can slip fit it and Loctite it in, which makes it easy to change because this is replaceable. You can heat the Loctite up with a propane torch or even a heat gun if you let it be on there long enough, and it just releases. And then these are hardened to boot as an added bonus. To boot, don't you know? These are hardened. I think these are about 45C. They're not soft. They're not, you know, they're not super hard, but they're better than just the soft steel. So that's another bonus. So those are kind of the reasons. Now, the challenges. Okay. So I've got a few to choose from. This thing's pretty thick, and I'd have to reduce the outside of this. And then how do you hold it? Oh, I got a point in the middle. And the reason I say this center point is important is putting it in the cylindrical grinder. You need a very accurately centered point that is, you know, coaxial to the diameter of the outside. So I could grind this down. Okay, so I got that one. I got this thing. Oh man, I didn't know I had this. So I think that's 1.25 inches. This is 1.1 inches outside diameter. And you can see the slot feature for the tang, the retention tang. So that's super neat. But if you look in there, can you see in there? It's an interrupted bore. It's got nicely polished bore in the front and then in the back, and then there's like a gap in the middle for clearance. A lot of spindle shanks and drill bits have a relief in the middle. So would this be good? Or would this be not as good as a solid all the way through uninterrupted center? I don't know. Seems like a quality piece. I could grind off the flange and just have it, you know, a straight socket. It's got a flat on the side for set screws, which I wouldn't be, you know, it wouldn't hinder me here nor there. It's got a hole in the side. That's probably for coolant. This is made to put in a turret tool post of a CNC lathe, so you can put Morse taper 2 drill bits in there. Okay. And then I thought, okay, that's good. And here's a 2-to-2 adapter. Oh, I could have showed you that. There's the male tang. There's the female socket. And this is nice too. This is ground. I could just cut this off. And I think these are about the same. Yeah, they're about 1.1 inches diameter. We got that one. Okay, sweet up, sweet. And then this one's like, I don't think this has ever been used. This is a Collis, C-O-L-L-I-S, and there's a number there. It's hard to read because it's a bit rusty. But look at that thing. I think that thing's, I measured it. It's just a smidge over 800 thousandths, like 802 thousandths or 803 thousandths. And, you know, black oxided, kind of nice, doesn't matter. But it's got the tang too. You know, I'd be cutting off the male part. And I'm leaning towards this because it's the smallest one, right? So I only have to do an 800 thousandths hole, or 802 or whatever, to Loctite this in there. I'm leaning towards this because it's the most minimally least, you know, it's the least invasive, minimally invasive to boring out that tailstock spindle. But you have to be diligent in covering your bases, and what I'm talking about is on any of these, this one or this one or that one or this one, who's to say, how do we know that that Morse taper socket is running true, running coaxial with the outside diameter of this? Because truth be told, this diameter doesn't mean anything in the intended use of this extension. It should be that the most important thing is the male taper is running true and coaxial and parallel with the inside taper, the socket. It should be, that's the most important thing. The outside really doesn't matter. So if it doesn't matter in its intended function, right, it might not be manufactured where that is actually made concentric with the female socket. This should be manufactured with the Morse taper tube bore concentric and parallel and with the outside socket, because that's what this is made to do. It's supposed to register on the outside and register on the Morse taper thing. Same with this. The intended function of that is for the Morse taper socket to run true, coaxial, concentric with the outside surface. So those two got a better shot of being concentric, coaxial than these do. But regardless of whichever I choose, and I'm leaning towards the Collis, the black one there, you have to check it. You have to measure it, because to assume you're going to make something, it may not work. So how am I going to do that? How am I going to check it? And think about it. That's quite the problem, right? How am I going to check that the socket is coaxial in parallel in every way with the outside surface? Well, I don't know. I've got some gauges, right? These are, this I got the 2 over there, but this is a 3. So this is a master plug gauge. Notice it's got a center there, and notice it's got a center there. So it was made on by spinning this on centers in a cylindrical grinder. I'm 1000% sure of that. Now the handle is just a knurled handle. It's it's a non-critical surface. It's probably not coaxial or concentric or parallel or anything with this actual taper. It's probably not. I know it's not. I know it's not. Just let me balance it there. I should probably store those in a better way, but whatever. So let me kind of show you my thought process to use one of these taper gauges as a tool to check if the bore is concentric with the outside of my adapter. The mighty Brown & Sharp 13, whank, whank. So what I did is I put this between centers, and I measured the knurling on the handle, and it was 0.632 or 631. I'm like, wow, that's like 6 or 7 thousandths above 5/8 of an inch. So what I did is I ground the knurl. I don't know if you can see that. Yeah, you can see it's shiny. I'm spinning it. See how it's shiny? That's the cleanup pass where I ground it. And look at the grinding wheel is black. That's all the metal that I ground, not all the metal I ground off, but it does deposit in the wheel. You know, whatever. So now that I've worked this 2 Morse taper master gauge, this plug gauge, this handle is exactly 5/8 of an inch, 625, and it is concentric and perfect and parallel and with the taper. Okay. So I can now put that in a collet or in a chuck, and this will run true. The taper will run true if the collet's true and the bore is true and the chuck is true and centered and the jaws aren't wanged or nothing. So this is going to be my test piece. This is a plug gauge. This is a master gauge. I'm going to use this now that I've qualified that knurled surface. I've qualified it in the grinder using centers. That knurled surface, it's less than ideal that it's knurled, but the surface now is perfectly cylindrical. I mean, I say perfectly, as perfect as I can measure. That knurled surface is perfectly cylindrical and coaxial, shares the same axis, right? Co-axis shares the same axis. That shares the same axis of rotation as the taper, right? Cool. So now I can use this master taper plug gauge to check my potential socket candidates for putting in my spindle. Now, I want to tell you a quick diversion here, a little story about setting this grinder up. You can angle the table for doing tapers, but really you can angle the table, you have to angle the table to get it straight. Okay. So I wanted to grind that little section there to 5/8, and it was only six or 7 thousandths over. So you constantly have to make a setup adjustment in order to get, not constantly, but you have to beforehand make an adjustment of this offset table to get the grinder to grind straight and parallel, okay, with the axis of the rotation of the workhead. And it is so sensitive, even though this tailstock is riding on a prismatic inverted V-way, if you move the tailstock, you have to recheck, you know, the taper that it cuts or doesn't cut on the workpiece. So I've had only 6 thousandths or so material to clean up. And what you do is you measure one side, you measure the other side, and it's not going to be the same diameter. And then you tweak the table and you measure and you measure. When I ground off 3 thousandths, getting it close, and then when I was getting down to the nitty-gritty diameter, I was a 1/2 thousandth big over here as compared to over here. So this was a 1/2 thousandth big. So what you do is, well, you'd have it, no, that's this one. You bring it in line, right? So if you're a 1/2 thousandth big here, you got to make a 1/4 thousandths correction. So what you do is keep it in line. You put a dial indicator. Okay, we're in line. Bam, right there. You put an indicator right there, and you adjust that knob until you see 2.5 tenths, right? A 1/4 thousandth here, right there. And that made me able to do it successfully. And it's interesting, if you look where the wheel is, and you look down, 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 it's like, that's an indicator holder. Okay, see? It's a plate with an indicator holder, and the wheel's actually right, like in line with that, I think. Right? If you go down, it's actually, the wheel's in line with that. So you put a rod up and a rod over, and then your indicator goes in. And you can measure, I measure here on the table, you know, whatever. So that was a side journey. So all right, so let's take a pause and come back and talk about the next thing. All right, back at it. So now that we've qualified that knurled handle surface as concentric and all that stuff, what I can do now is I can take that, right, and I can chuck this in a collet or in a 4-jaw chuck or something, get the gauge running true, and then stick an indicator on the outside of that, you know, socket, and see if it's running true. And if it's not, take a cut on it. If I do this in the lathe or the grinder, it doesn't matter. And if it measures out, I might be able to just use it as it is. So that's the idea of making the tapered mandrel and all this stuff. So, oops, whacking my calipers there. All right, so now let me go set up that tapered plug gauge in something and spin it, and we'll see what it does. So, bring you back. All right, guys, let me show you a little problem that I'm running into. Okay, we've got the mighty Pratt & Whitney lathe, and I've got my freshly ground and verified plug gauge in this chuck. Now, it's a 3-jaw. I mean, it's a 6-jaw, but it only has 3 jaws. And the jaws are freshly ground with the tool post grinder. These jaws are minty. And this is a set true chuck. So, you know, you can adjust all the, there's 4 adjusters like a 4-jaw would have. And I want to show you this. Okay. So you can just see I'm spinning the chuck. So that's 1 and 1 and almost 3/4 thousandths. All right, 1 and 3/4 thousandths. So like 1.7, 1.8 thousandths. That's a lot, right? That's a lot. So I'm indicating the tip, the small end of the taper. So let me bring this back. Let me crank forward, and I'm going to measure right there at the big part. Now I'm going to move this in with my finger. I'm at 1 thou. Let me go 1 revolution. There, I'm back at 1 thou. I got the oh my God. I got the chuck key hole on top. All right, I'm gonna do it one revolution again. There's another rev. So I'm off like a couple tenths. All right, let me zoom. All right, so the problem is, if I'm basically concentric at this end, I'm out almost 2 thou here, right? So even though I ground these jaws, I have a set true chuck, I'm getting it, I can make it concentric here, but then I've got angular deviation at this end. And I mean, it doesn't matter. If I set this end to 0, because of the angular deviation of the chuck jaws, then this end is going to be 1.5 thou, 2 thou out. And I'm going to tell you guys, I fought this with a collet. I had a collet, a 5C collet. I had a 5/8 5C collet in this lathe, which has a really good spindle. I tried 3 different collets. Was it 3? 1, 2, 3. Yes. 3 different collets. With these 3 collets, I've got varying degrees within 1 thou of radial run out and angular run out, using 3 different 5C collets. This grinder has a 5C spindle nose also. I've tried the same 5/8 5C collets that I happen to own, and all 3 have different degrees. All my 3 collets that I tried have some amount of radial and angular run out. And the same with this darn freshly ground chuck jaws. So you're going to say, Doozer, it's probably your test piece that you made. I don't see how. Because if I've put this plug gauge on centers back in the Brown & Sharp 13, and you can indicate the taper part, And anywhere along this taper is 0 for 0 using the center points. This is 0 for 0 for 0, perfect, within half a tenth of run out. And then I ground the knurl handle, which has got to be. You cannot have it be out if you're on centers, and this is measuring perfect on the taper, and you grind the handle part and true it up, and it measures within, you know, a 1/4 thousandth of the same size on both sides. I don't know what's going on. I don't know why I'm having so much trouble here. Because I got to get this thing perfect radially and axial doesn't matter. Radially and angular run out perfect. I don't know. I'm going to think about this. Maybe I'll post this and you guys can give me some ideas. I just need a... The next thing I'm going to try is I've got a ball bearing Suburban spin jig spindle that is made to go on the magnet of the surface grinder. And I know that thing is dead nuts, dead nuts, dead nuts. So in case that spindle's off and the Sagami spindle's off, then I know this Suburban spin jig is perfect because I've tested it multiple times. So that's going to be my next avenue. We'll bring you back. All right, guys. I did this. I want to show you what I got here. So I got the Collis extension that I want to use in the Brown & Sharpe 13. So the center point is just barely big enough to catch the actual Morse taper, and it's got a center point, it's got a center hole for a tailstock center in the butt end. So I've got it set. I'll turn the camera sideways here. I'm trying to show. So I'm at 3. And it's a rough surface. I'll go slow. Two-tenths. Okay, so let's say I'm going to turn one turn. So there's like 2/10, half, back to one turn. So I've got about 2/10 run out on this thing. That's perfect because I'm referencing inside the Morse taper, and it was originally manufactured between centers. So this whole outside diameter, and there's a little bit of rust, and there's a number engraved on it. If I can get, come on, focus. See, it says Collis, and then 7.5, 2, 5.7, 2 Morse taper. It's got some schmoo to clean up, and I'll go over it with an Arkansas stone or something, or an India stone. But I'm satisfied that with the Morse taper bore is concentric with the outside, because otherwise this would be just womping around like just silly. So I don't have a solution to, you know, what I was trying to do with my mandrel exactly. And precision is tough, man. It's just a tough business. But the thing I want maybe you guys to take away from this video, for something to be truly spinning, you know, round and whatever on an axis, it has to have not only be concentric radially, right? So radial is in-out movement, right? That's radial, along the radius. It has to be aligned in an angular orientation as well. And if you have radial concentricity here, and you have radial concentricity here, that means that you have angular concentricity, right? Axial concentricity is this way. So I'm not really concerned about axial or end float with this situation. I'm concerned with radial and angular. And if you've got good radial run out there and good radial run out there, that means your angular is 0. You have no angular deviation if you can measure at both ends and have, you know, 0 or close to 0 radial run out. Okay, that's all I wanted to say. I'm kind of satisfied with that. I'm going to go with this. I'm going to cut the male part off. I'm going to stone all this. It looks like it was, this is before laser engraved. This is like vibratory punched. Like there's a raised up from the surface. This is a dot matrix, mechanically, physically engraved. I'm just going to stone this off. I'll take off some of the black oxide, but I don't care. Alright, this is way too long of a video, but we explored some good subjects here, I think. And on to the next. Alright guys, not sure where I left off, but I wanted to record this. Okay, now after all the rigmarole with trying to get my Morse 2 plug gauge, taper gauge to spin both concentric radially, trying to think here, radially and angularly, if that's a word. So I've got my Suburban spin jig, right? I think Simco used to make these, and then Suburban bought Simco's design and they shortened it, and they you know, they painted it red. But anyways, this is a 5C capable like little spindle guy. So I've got a Harding brand 5/8 collet to match what I ground on the knurled handle, okay? And I've used this collet. I've got 3 collets, 2 Hardings and a phase 2 or something. And look at this. Alright, so I'm going to spin this, right? I can't get it all in the same shot, so you're going to have to take my word that I'm spinning this. And I'm trying to zoom in. I've got like 1/2 tenth, man. Okay? I got 1/2 tenth. You can see it going around. 1/2 tenth, man. And I'm going to stop spinning it. I get 1/2 tenth, you know, there at this side or right at the tip. I mean, this thing is just balls accurate. This is amazing. This is the same collet that I used where I was having trouble in the Sagami lathe and in the Covell cylindrical grinder. So that tells me that this collet's fine. It's just the spindle nose in the Sagami lathe and the Covell grinder are off a little bit. They could be reground. The Sagami's only off, I don't remember. I think it was pretty good for radial, indicating at this side, but angular it was off 1/1000 or 1/8, I forget what. But on normal work, that Sagami just does a bang-up job. I'm surprised to see it off that far. Of course, I just do short work on the Sagami. But, you know, the spindle on the Covell being, you know, having this run-out situation, you know, a grinder you want as accurate as this thing. You don't want freaking no run-out at all. You want that thing to be just balls accurate. And like I said, this thing, man, and I promise you, you know, I'm preload. I mean, the indicator's set right. It's not like I'm trying to fool you. Because the whole point of this video is to show exactly what I got, and you know, try to get down. So where was the thing? Yeah, I stuck this on there, and all right, well, frig nuts. Let's do this here. And I just gave it a little bit. I didn't smack it home like it's baseball season, right? And kind of. Alright, there it is. So you can see so I stoned off the lettering. Let me zero this. Okay, hold on. Alright, so that's trying to adjust my height gauge. Oh, gee, it's so freaking sensitive. Well, alright, so that's kind of, I'm spinning it 8/10. No, I'm not zeroed. It's so hard to do. Alright, let's spin that. Yeah. It's just like a little dip, but mostly this thing is within 4/10. And I think it's pretty consistent. It's got a whoop right there. I don't know what the fridge that's about. Alright, let's see here. Let's do it right, sorry, right there. Let's see here. And who knows when we spin it. Right? So here I am, approximately at the other end. I'm within half a thou there. I'm going to say the whole thing is within a half a thou. And at the part I ironed down, I stoned down. That's so that is that low? Yeah, that's low. That's the low point, and then the high point is about 180. So low is about there. High point, yeah, so I'm still a little bit high where I stoned off the, you can't see it anymore, it said callus. I might rub on that a little bit more. But anyways, I'm within a 0.5 of concentricity between the internal Morse taper on that callus adapter piece and the outside diameter, the straight outside diameter. So that tells me I am good. I'm going to cut off the male portion, cut it off, grind it off, whatever, and that's going to be good enough to glue, I say glue, Loctite into my spindle. After all these permutations of figuring out how to measure this thing, that's where we're at. And the most accurate spindle I have is this Suburban spin jig. And you know, kudos to the Harding brand 5C collets for being within a 1/10 or whatever that they are. But that's what I was trying to do.